Aside from solar PV systems, another way of producing electricity coming from the solar radiation or solar light is through the concentrated solar power system or CSP. So in this system, we can also generate electricity by focusing the sun into to achieve a really high temperature to a suitable fluid to operate a heat engine. So in this case, instead of converting the solar light directly into electricity, we are actually concentrating by using mirrors. So we use a mirror configuration to concentrate the sun's energy into a receiver, and normally this receiver is a form of a fluid. So this could be various types of fluid like oil that can absorb the heat, and then this heat is used to drive um, to drive or to drive steam or to create steam, I mean, and then this steam is used to drive a turbine to produce electrical power, just like in a conventional fossil fuel power plant. So we make heating, and then the heat produces steam and then drives a turbine. So the main thing about the CSP is that the lenses or the mirrors are very important aspect here, because we need to concentrate the sun's rays into a specific area so that it can generate heat, a lot of heat. So this heat, as I mentioned, causes the liquid to boil and expand, and then make steam, and and generate electricity by driving a turbine. So on another thing about this one is we can also store the thermal energy coming from the sun. So instead of using it all the time during the daytime, we can store the thermal energy and use it only at nighttime. At the time, then we need more energy at night. So we can store this one in a fluid liquid or in a molten salt, for example, and put it in a storage tank for use at various times of the day, especially the nighttime. So in this system, there are four types, and there are four kinds of these. We have what we call as the parabolic trough. So we have this system here, the parabolic trough. We have the Fresnel system, the Fresnel lens. We have the parabolic dish, and also we have the solar tower or the central receiver. So these four different types are, they have pretty much similar functions. And as you can see, this parabolic trough is the most mature, and more than 90% of the commercial concentrated solar power is based on parabolic trough. So it can generate electricity temperature up to 400 degrees Celsius. It means that the liquid is actually moving towards this tube here. So this is the tube where the liquid is the working liquid is moving, and so the sunlight goes towards the mirror here. So the mirror is like a convex type here, or concave, and then the system is designed that all of this part of this curve will reflect back into this tube here. So if you remember, when you were a child, we tried to play with magnification glass, and so with magnification glass or any glasses, and we want to burn a paper, for example, we want to concentrate the sunlight onto a specific area of the paper, right? This is the same way here. Instead of burning, it stores the energy here, so it generates heat. So the fluid that is heating here goes towards a boiler that power the steam, or to produce steam towards the powering of the turbine. The same way, the Fresnel is similar with a parabolic trough, but they use a Fresnel lens. So these are some horizontal lenses that also can move, so that it can move individually here, so that it can redirect the direction towards the central receiver here. So this is the form where the working fluid is again moving. So it's pretty much similar design with parabolic trough and the Fresnel lens. The other one is the parabolic dish. So this is a dish type, and we have the absorber as the center of which a small absorber. So in this case, the absorber could contain some gas that could be heated up by the sunlight here, and this gas will power a Stirling engine, and this Stirling engine will be the one to produce electricity. So this is not mostly used in commercial purposes. This one is more mature now. And the last one would be what we call a solar tower or the central receiver. So what happens here is that the system has a large area of mirrors here. These are mirrors or heliostats. We call these heliostats here or mirrors, wherein the sun will shine, and then all of the reflected light from the mirrors here will are designed to go towards a central receiver here. And this central receiver has a circulating molten salt or other fluid that could absorb the heat. So the molten salt is heated because these molten reflectors are not molten reflectors, but these heliostats or mirrors are actually tracing mirrors. It means it can move. So depending on where the sun is shining, for example, if the sun is here, the mirrors will also move towards the sunlight so that it can go towards the direction of the absorber. So these mirrors are actually moving. These are not fixed. So the central receiver is a lot of mirrors around surrounding it. It could be the circumference here, but in most cases it will try to heat up a molten salt here up to more than 500 degrees Celsius, and this molten salt will be used to heat up water to generate steam to power a turbine, or they can also be used to thermal storage of this heated salt to store at different times of the day to generate electricity if needed. All right. So we can see that the temperature now, if comparison with solar PV, the solar PV has a requirement of very low temperature, and the ideal one would be at 25 degrees Celsius. So it's low temperature. This is that's not concentrated solar energy. So we use just the radiant energy to directly turn the light into electricity. But for this case, we are turning the light into heat first. And then the heat is powering the production of steam towards the powering of the turbine to generate electricity. So from there, we have a linear focus concentrations, which is this one. So this is a lower temperature that can be achieved. And then now the solar absorber is where this is more point focus. So the absorber here is the same. This is now the point focus up to almost 1000 for this. And this one is around 500 to 600 degrees Celsius. So this is the difference in temperature need for each of the various technologies. So let's see more in detail about this one and this one, because these are the two most commonly used now. This one is the most mature and commercialized. So 90% of most of the solar thermal or solar concentrated solar power is based on this one. And this one now is the solar tower is the most growth this year. So it's a lot of potential for large scale production of electricity. And in Australia as well, we are constructing a number of these concentrated solar power for us to have more energy security as a way of contributing to our energy mix. So the parabolic trough, as I mentioned, has a collector, a concentrated this collector here. So the liquid is actually recirculating, just recirculating towards this part, and there is a heat exchanger, wherein the heat exchanger contains water on the other side that could heat up and become steam, and this steam powers the turbine here. So the steam is powering the turbine, and then turbine powers the generator to generate electricity. So what happens that the working fluid like oil or some other fluid that goes towards here that can absorb and heat it up to 400 degrees Celsius by the mirrors here goes back towards the heat exchanger, and so this is hot side now. So it goes towards here, and this is cold water here coming in. So the cold water heats up because of the heat exchange over here, and so in the water heats up and becomes steam, and then the steam powers a turbine, and then powers a generator and generate electricity. So you can see from this part here, cold water comes in or cold fluid comes in, being heated up and goes out as hot fluid. So this is the mechanism for parabolic trough. So it's a line concentrator. So you have a line system here that is concentrated by the solar radiation, reflected back on that specific point. The other part that I would like to mention is the solar tower, and this is one of the fastest, not the fastest, what the most growth that we can see from based on a solar thermal or concentrated solar power system. So what happens here is that, as I mentioned, the heliostats are used, and these heliostats are not fixed. Please remember, these heliostats are moving, so they move accordingly where the sun is shining. For if it's here, they have to make a certain angle so that the reflection will go towards the center of the receiver. All right, so the height of this receiver is almost 200 meters high, and it uses usually a molten salt system, so that because the molten salt system can absorb much of the heat, so it can heat up really fast. So from here, for example, it goes up, is being heated, and goes down at a much higher temperature. So it's around 565 degrees Celsius now. It goes back here and then towards a steam generator evaporator. Um, so it heats up this system here to generate steam, and the steam goes towards the turbine, and so that this turbine is now powered by the steam. And so once the turbine is powering, it also powering the generator to generate electricity. And so the system goes that way. So the molten salt is just recirculating back towards the thermal storage system and goes back towards here. So we can store the energy here as well at a certain temperature if we need it at a different time of the day. So for the solar towers, the biggest one in the world that has this a big capacity is in Spain, and this is an example of a concentrated solar tower. So we can see from this picture here, these are heliostats that are surrounding the solar tower here at the center. And so all of these are spaced appropriately. They should not be too close with each other. So the farther you go from this distance towards here, the spacing should be farther, because if it's too near, they can make a shadow from this part towards the front side. So it has to be at a good distance from each other so that the light reflection can go towards the tower, at a very focused one, so that it can heat up the tower. So all of these heliostats are moving, all right? So they can move left and right, up and down, so that it can follow the trajectory of the sunlight. So these are some examples as well of other areas where the installation of concentrated solar power. So this is a Jima solar plant in Spain. So in terms of the economics of the concentrated solar power, we can see from here that still the concentrated solar power, if you can look at the previous slide, you need a very large area, and you need a lot of heliostats and a lot of system in terms of building the tower, as well as some storage systems, as well as on connection with a power plant. So in this case, the capital cost will be quite high. So we have a capital cost. If you compare with this capital cost for nuclear, like for example, it's 5,500 per kilowatts. But in this case, you can see that the tower is around 8,000. It's even higher than the nuclear here. Onshore wind is around 2,200. So you can see that this is pretty much expensive for the concentrated solar power. The capacity is quite high, so it can produce a lot of power, but it also needs a very large area. So in this case, if you compare with a parabolic trough, it's only around 7 or almost 8. But if you go for tower here, if you want to generate really large electricity, then you need to have a really large area. In this case, around 14 square kilometer. All right, and in terms of the cost, in terms of LCOE, you can see that the LCOE for the tower is around 12 to 17 and 14. So in comparison with the solar PV, in which case the solar PV is around 4 to 5 cents per kilowatt hour, then this is not even close. So it means that it's not competitive in comparison with the solar PV, because the solar PV has been, a lot of production, a lot of uptake already, and so that's why there's a much decrease in terms of cost. But CSP is one of the major, how to say, the major approaches now that we are doing in Australia for large scale electricity production based on solar energy. So this is still a very promising method to provide, to contribute for energy security in Australia. A short video is provided in the next slide to show the some aspects of the concentrated solar power or solar tower.
The problem with renewable energy is the lack of continuous supply. Solar power only when it's sunny, wind power only when it's windy, and wave power when the sea's not too rough. I'm Russell Beard and I've come to South Spain to visit Gemma Solar, the first solar tower power station that can produce electricity 24 hours a day. But in order to get a real sense of the scale of this place, I need to get a little bit higher. Samuel!
Wow, my heart is in my mouth a little bit, but it's incredible. And I can't believe I'm flying this plane. So Sam just spotted the tower up ahead, so he said just point at the tower and carry on. Okay, here's Gemma Solar. You can see it just below us now. Thousands of these heliostats, these revolving mirrors. It's just amazing. Feels like we're looking into the future.
Photovoltaic is like one of the fastest growing energy sources in the world at the moment, but these aren't photovoltaics, are they?
No, not at all. They are not photovoltaics at all.
So these
Those
are just
glass, are mirrors, and they are reflecting the light on top of the tower.
The reflected sunlight from the 2,650 heliostats combined can generate enough electricity to power 25,000 homes, but only if they're all pointing in exactly the right spot.
Santiago's brought along one of these miniature parabolic mirrors, which I guess is almost like a perfect scale model of your solar tower.
Yes, I mean the tower looks like in the middle of a circle of heliostats, and every heliostat is like, taking a different angle to reflect the light on top of the tower and then to concentrate all the energy on a single spot.
So let me try.
It's going.
Oh wow, you can see it catching fire. It's so sensitive, like one tiny degree out and it stops burning. I mean, this must be the challenge that you're facing.
Exactly, I mean, exactly what we have to be doing. I mean, we have to be very precise in moving the heliostats in the right position to concentrate the light there.
Sunlight is reflected from each heliostat onto a central receiver at the top of the tower. Sodium and potassium nitrate salts are pumped from the cold salts tank up to the receiver, where they absorb the concentrated solar thermal energy, reaching temperatures of up to 565 degrees. The heated salts are then pumped down to the hot salts tank, where they can be stored in a molten state or used to generate electricity via the heat engine.
This is the hot molten salt tank that contains the molten salts at 565 degrees. This is like a big battery, but it's a thermal battery. It's not an electrical battery. In fact, the energy which is accumulated here is enough to continue operating the turbine for 15 hours at full speed.
So this is what distinguishes this place from other solar tower generators around the world. It's actually that storage.
Exactly.
Being able to store energy this way means that solar power can, for the first time, be provided 24 hours a day, not just when the sun's shining.
This is the vessel in which the water becomes steam. Inside you have water at maybe 500 degrees centigrade and already 100 bars of pressure.
This is incredible. So what Santiago's telling us is, despite how futuristic this all looks, the actual business end, where they create the electricity, is much the same as any other coal-fired or even nuclear power plant. So see, it's a steam-driven power plant. Wow.
Wow, this is what I'm talking about. Now this looks like a power station.
And it is.
This technology's been around for hundreds of years, yeah?
Yep.
And so it's really out there, it's the only sci-fi part of this building. By the time the power comes down from the molten salts, we're talking about good old-fashioned steam turbines, and that's what we can hear now. And you can even see it coming out of the little chimney at the top.
We are going to be reducing our costs, but also due to the fact that the oil prices are going up will make it impossible to burn gas to produce electricity. And then our plants will continue to be delivering cheap and clean energy to our children, let's say.
So these are some of the various installations of concentrated solar thermal or concentrated solar power. You can see that there are a number of countries already working on this one. Australia is also trying to construct a number of these solar CST projects. And so the blue ones, as we call it, operational, the red one is under construction, and the green one is development. So we can see from here that among all the different places, Spain is leading this case, 100% of operational in Spain. Other countries are already developing it, but others are just under construction. Probably 34% out of this estimated total capacity, which is larger than Spain, but still only 34% is operational for USA. But now, of course, has been continuously growing, because this has been this map. I think it's just a few years back. So now the updated ones would be a bigger portion actually are growing from other parts of the country. Australia is also growing in terms of the projects on CST. So this is a major contribution towards the sustainable energy future of Australia as well. So in the solar power in Australia, we are receiving a large amount of solar energy, and solar, as you can see, is red here. So that's why we have a lot of bushfire, because of too much heat coming from the sun. So solar power is one of the best avenues or best contributor towards our energy security in the future. So far, we have installed almost 6,000 megawatts of photo PV solar power. So a lot of these megawatt powers are coming from home base and a number of solar farms as well. And the PV is contributing very large amount now of percentage in terms of electricity generation. So it's increasing now. It's around 4 to 5% already at this point. And if we consider really all over the Australia, then we are receiving large amount of energy coming from the sun. And so it is but right for us to actually consider much the use of solar PV and the use of concentrated solar power as well, for us to have more energy security, at the same time to take care of our environment, because this type of technology has less greenhouse gas emissions, and it will be more environmental friendly, which we are going to talk about its environmental impacts in the next few slides.